Hi, and welcome back to Spherical Chicken in a Vacuum. Today, I want to go back a little bit on the topic we were speaking about on the last lesson, which is crystallinity and the structure of material. Okay, the material lattices in particular. Okay, and if you remember, well, at the beginning of this course, we were speaking about objects and how we can split them in their shapes and their materials. And if we just look at the materials, they are composed of atoms, and those atoms can organize in different ways. Okay, and these ways can be summarized in a list of lattices, most common lattices that can be found, like this cubical face-centered cubic structure here, can then be used as a unit, and if they are multiplied in every direction, they can build up our solid, our object as a whole. So the object can be split like Lego blocks into units, and each unit will look like the crystal lattice that we discussed at the beginning in the previous lecture. Okay? But someone pointed out in the comments that the story is not this easy. They claim that I forgot to speak about amorphous structures, the structures in which there is no ordered and organized repetition, longer term um, repetition of units. So basically, structures in which the material is not well organized. And this makes sense if you think about glasses. Glasses are amorphous materials. They're the most common, probably, type of amorphous material. And their properties, everything about them is about the absence of an order inside. There is no long-term order inside most of the glasses. There are some interesting exceptions, and we will talk about glasses in a lesson in a few weeks, I think. But let's go back, let's simplify, let's talk about something that we all know, which is, again, Tetris. If we are playing Tetris with a really kind software, the software might give us a lot of easy elements like this yellow square unit here. And to organize the yellow squares is very easy. You just need to make lines of them, multiplying them on one line until, wow, you get the line collapses. And you can go faster, as fast as you want, as the levels increase in difficulty, and still you will be easy. It will be easy for you to organize your squares in a nice structure, nice regular structure. That is the crystalline structure of a material in a way. Okay, if the software gives you more complex shapes like this T, then you need to use your brain a little bit more in order to properly organize them. Imagine you have only T's. It's difficult to make a straight line only by T's. You need to use your brain. And as the speed increases, it gets more and more challenging to be able to do so. In this way, what happens is that you're more likely to make mistakes, and the structure, the elements that you see on your screen get more and more disorganized, just like, in a way, amorphous materials. Okay? And these are very simple units. If we use the example of the Tetris with five square elements for each, five square units for each element, which I think is called Tetris 5. I will not give you the animations, but you see, it gets more and more challenging to even make one straight line that you can then cancel. So the structure appears more and more disorganized and chaotic and randomized because of the shape of the elements. So you see, there are two things here. There's this complexity of the element itself, and there is the time. As the speed of the game increases and increases, it gets more difficult for the user to be able to sort things out. And this happens in materials, and that's why we have amorphous materials as well, like crystalline materials. Okay, but let's have a look a little bit more in deep into crystalline materials. Okay, imagine that we have three crystals that are growing. this is a liquid material, it is cooling down, these crystals are forming and they are growing and growing and growing until they occupy all the screen. In this case, at the beginning, we have three crystals, one orange, one blue, and one green. And with time, as the temperature probably decreases from the melt status, some solids have been formed, and those solids are those crystals that we are seeing here. And depending on how many crystals we form, we can have one single crystal, for example. If only one crystal nucleates, maybe at the center, for example, at the center of the screen, then it grows slowly without any crystals forming. In the end, we can end up with a monocrystalline material. If many crystals are formed, we have a polycrystalline material. And the rate at which new crystals are nucleated, so they are born, at the rate at which they grow up, decides basically which is which material will be a polycrystalline, a nanocrystalline, a monocrystalline, amorphous material. Okay. In the case of the amorphous, we don't have a crystal that grows in a regular way, in a regular shape, like these ones. You see that all these balls are in order here. Okay. There's another thing I want to show you. Between these crystals, there are some empty spaces. These empty spaces are called the grain boundaries, and depending on the amount of grains, the amount of grain boundaries increases, and the grain boundaries have their own properties, and they can mess up with the properties of our material. For example, let's remove completely our grain boundaries, and let's shine a light through our material. If it's something like glass, amorphous glass, there is no grain boundary in the between, and the rays of light can go from one side to the other side without encountering any obstacle in the middle. If the material is a crystalline material, things change a little bit, and the light finds these grain boundaries. These grain boundaries scatter the light in many directions, reflect some light, and in the end, you will have less light on the opposite side of the material, for example, or your material could be completely opaque, so no light can shine through your material. There are other reasons apart from grain boundaries that cause this kind of phenomena, but in this case we are speaking about crystalline structures, so it's good to mention grain boundaries. And if you look at this is a femoral head. It's pink, and it's basically a ruby. The reason why it's not transparent and shiny and red, with a strong red, is because it's a polycrystalline ruby. If it was a monocrystalline one, we would have transparency and a stronger red color. Instead, we got this nice pink. Okay. Now, we mentioned that there is the elements and there is the speed inside, or the times. And what the speed are we speaking about? Well, it's the cooling down speed, basically. So take for example this graph. Let's start from the top. Imagine that we have a molten materials of some kind, and we cool it down very, very slowly. What we might get is a monocrystalline material. If we cool it down a little bit faster, we can get a few crystals. If we cool it down much faster, we can have a lot of crystals. Nanocrystalline materials are one example of materials that where the nucleation of grains it's huge and the growth is very little. So again, we have two types of two time-related parameters here. One is the nucleation rate, which is the amount of grains that are born, let's say, and then there is the growth rate, so how fast they grow. If we nucleate a lot, we have small crystals and a lot of small crystals. If we nucleate slowly, we have a few bigger crystals. If you go very slow, we have one crystal, like in jewelry or, for example, in energy applications. For example, turbine blades can be monocrystalline. Okay. If we cool down very, very fast, we don't give the time to the material to find an order, and what we get is an amorphous material, like in the case of glass. Okay, so as you see in this graph, the line, the cooling rate, the orange line of the amorphous materials does not touch the crystalline region, the crystal region. So it means that it doesn't form, we don't have crystals inside of our amorphous material. And I say that the element plays a role, and we saw it with the pieces of the Tetris puzzle, right? Well, some elements are better at forming glasses than others. And silicon oxide is one of those examples. In silicon oxide, it doesn't matter how slow you cool down. Well, it matters, but it matters much less how slow you cool down your material, because silicon oxide wants to be amorphous, prefers to be amorphous. You need to be very, very slow in order to avoid this effect. Water, on the other hand, prefers to be a crystalline material. And silver, it's even more stubborn in that, meaning that it's very difficult to make amorphous silver. You need to go to very fast cooling rates in very special, peculiar experimental conditions. Okay, just to give you a few rules on what changes from the point of view of the basic elements is that good glass formers have low atomic mobility, meaning that once they form their connection, they don't want to move from there anymore. That's why they cannot rearrange to give space to the other atoms to organize a very nice or regular structure. They are messy. They want to stay there, and they're difficult to move. They have strong bonding, so you cannot break the bond, take the element away, and put it somewhere else. And they form complex crystal structures that take a lot of effort to make. That's why, for example, quartz and cristobalite are much more difficult than glass to obtain. Okay. The other end of the spectrum, we have bad glass formers. They have high atomic mobility, meaning that it doesn't matter where you put your atoms, they will move to reach a position where they can have order. They have weak bonding, meaning that they can break and form bonding to other atoms and reorganize themselves to a more suitable position. And they form low energy crystal structures like the face-centric cubic we saw before. And that this means basically that they're organized better, they take less space, they take then less energy, they are more compact, and that's why they form easily this nice regular structure. And it doesn't need to be one or the other. There are materials that are semi-crystalline, so partially crystalline, partially amorphous. And even if it's a little bit of a stretch, some polymers, many technological polymers actually, are partially crystalline and partially amorphous, for example. So you don't need to pick one side actually. But the basic concept is that being amorphous, it has little to do with what you like as your lattice structure. It has more to do with how fast you were cooled down from the melting temperature, how much time, how much energy you had to reach a nice order, which is related to your basic properties. But we will speak about glass and a little bit more about amorphous materials in the next lesson, I think. For today, I think this is more than enough. Thank you for listening.